Thank you. Well, this is the abstract for this talk. I've been working at Satellogic for the last 2 years, mainly on stuff that has to do with image acquisition and image processing. And I will tell you and show you a little bit of that. But first, I want to tell you a bit about Smalltalk, about Cuis. To me, Cuis and Smalltalk are synonyms. Okay, give me a second, please. I prepared the slides in Spanish and I will talk in English in the hope that this will make stuff easier to understand. Let's see how that works. Okay. These are some thoughts I had in 2008. It was the time that Squid was stuck and Cuis and Pharaoh were born. So let me tell you how Cuis got started. Squid Central, the dream team led by Alan Kay and Dan Ingalls, was formed to create Squid. A few years later, they went on to new adventures and left Squid in the hands of the community. But it was too much for the community. Nobody dared to change the code. Just small details. People thought that the best they could do and the only they could do was to be guardians of this heritage. The Squid community behaved a bit like Europe in the Dark Ages. The ancient Greek had been the highest point in Occidental civilization and were considered the only authority and the only source of all knowledge. For Europeans of the Middle Age, to study meant studying the classics, not looking at the world. Things have changed a little bit in later years, but still Squid evolution is limited by the need for backwards compatibility with old code. We still venerate the ancient Greeks, essentially because we could not yet attain such a clear vision of the world as they had. We are still prisoners of our own ignorance and the superstitions emanating from it. Our challenge is to build Renaissance and Enlightenment, to lose fear, by means of study and work, to recover the classic knowledge, to put it in proper perspective, understanding the limitations of its time. This also includes discarding things like antique religious and mythologic beliefs, knowledge that can be replaced with better, more advanced knowledge, and an old folklore that is no longer part of our culture. It's not completely forgetting about them, but to put this in proper historic, to put it in perspective, giving it its proper historic value. I mean, the theory of the 4 elements is not part of modern chemistry, even though we all know about it. Unfortunately, path to modernity might require hyper-specification, an ever-growing number of specialists that know each time more about each time less. And an army of historians, sociologists, epistemologists, not just to understand the system, but to understand the huge and heterogeneous society that builds it. Maybe the solution, at least for the kernel of the system, is not to go much beyond Renaissance, where dedicated and talented people tried to practice all the arts and sciences at the same time. This is not a new idea, it's the personal mastery principle from Dan Ingalls. The smalltalk kernel should be simple and small enough to fall between the reach of a single person. So, where do we want to go with Cuis? What is the logical evolution of smalltalk 80? I want to tell you a little bit of old history that maybe all of you already know, maybe not. The origin of smalltalk and the idea of personal computing is the Dynabook ideal, as thought by Alan Kay in the late 60s and early 70s. The idea of a Dynabook is a new kind of musical instrument whose music is not sounds but ideas. A computer can fruitfully process any kind of existing media. Computers are used by all kinds of artists to work more comfortably and to be more productive. The first person who realized this was Alan Kay, and this vision of the Dynabook was the guide for all the work they did at Xerox Learning Research Group in the 70s. He realized that this new media that could encompass all the previous ones was not just a media but a metamedia. This means that it can produce new kinds of media because it's completely malleable. And even more than this, he thought that there should not be any need for specialists to make all this happen. Any user of a Dynabook should be able to create his own kinds of media and adapt existing ones to his own needs. So building a Dynabook was the first objective, the main objective of the Learning Research Group. Their first system they built, Smalltalk 72, was the first draft of the software for a Dynabook. And they actually tried to use it with end users, with primary school kids. They found two kinds of problems with Smalltalk 72. The first one was that it was too hard to use for kids, and the second one was that it was not powerful enough for professional programmers. So they kept building new systems, making them each time better for the professional programmer, and never went back to use Smalltalk as an end-using programming. They used it to build end-user systems like Playground, eToys, and Scratch, systems that are within the reach of an end user but not powerful enough for a programmer. So the real Dynabook was left as a dream for the future. But we are lucky. We programmers are privileged people because the Dynabook does exist, but it exists only for us. Smalltalk 80 and its offspring are real Dynabooks, if the user is a Smalltalk programmer. Because Smalltalk eases the activities we expect from a Dynabook. We expect to to be possible with a Dynavook. Smalltalk allows the design, simulation, experimentation, and documentation of active knowledge. The Cuis project explores the possibilities and reality of Smalltalk as a programmer's Dynavook, an universal processor of ideas and knowledge that lets the user run any system of ideas or artistic expression he might build or think of. We want to keep walking the path that Daniel showed us. The possibility of having a real Dynavook is too good not to follow it. So this is the main objective of Cuis and the guide to many design decisions. Cuis also wants to be a Dynavook for other people, for anybody, not just me. So these things are important. It must be usable on any common platform. It must be platform agnostic. It must be open source. It must be free of patent issues. I heartily recommend you to take a look at that URL, defensivepublications.org, and the anti-patent movement. Cuis also wants to encourage and support a community of users and contributors. If you want to know more about why we do Cuis, please read Design Principles Behind Smalltalk, and if you also have a bit more of time, read Coders at Work. This doesn't want to work. Okay. At Satellogic, my duties were to explore problem spaces, to learn, to experiment, to implement stuff, to document what was learned, to solve problems, to answer questions, to develop frameworks and applications. What could be better than a Dynavook for doing this? So Cuis is the Dynavook I use. I will now show you a couple of the things I've been working on there. Okay, Hera, you will have to forgive me because I stole this from you. Okay.
I don't know what it is, but you're from you.
Sorry. It's only on my screen, so here it is. 1 second, please. Okay. At Satellogic, we build satellites, small satellites, and this is from a presentation Hera gave a little time ago. Our first satellite, Captain Beto, is in low Earth orbit, like you can see here. This is Captain Beto. It's 20 centimeters high and weighs about 2 kilograms, and this is our second satellite. We called him Manolito. This second satellite has a camera for taking images, and I've been working on it. So, well, I've been using Cuis for doing lots of kinds of stuff. One of the things I did was a software radio. We had some trouble decoding signals from our first satellite, so I tried to decode them from Cuis. So I built a chain of signal processors good for this kind of work. I don't have time to enter into too much detail. I'm just showing you these pretty pictures. This is a signal that we get from the satellite, and these different colored lines are the output of several decoders I built. This goes to a digitalization step that tries to decode zeros and ones from here. These are zeros and these are ones, so it kind of works. This one was a bit a harder signal, the kind of which we could not really decode very well, and maybe you can see why. Another thing I did at Satellogic, we had this very interesting camera technology called Foveon, that is a multispectral camera that works very differently from all the common ones. They don't publish how they work. For doing some experiments, I had to kind of model the behavior of the sensor, the response to light at different wavelengths, and these fixed lines are from a documentation from the sensor manufacturer, and to these lines I used Cuis to match these thin lines, blue, green and red, and from the formulas for these lines we could extract the real behavior of the sensor and the algorithm we had to apply to reveal the actual colors of the images. So.
Sorry, this is implicit or is the formulas are good?
The formulas are, this was a typical use of a dynamic. It doesn't have to be too fancy, it just has to be comfortable and flexible. I knew the kind of formulas that could fit them, and I just kept adjusting the parameters by hand until I got a good result. This is easy to do if the environment is comfortable and quick, and it's harder if not. I did several image processing stuff too. We have a big problem while taking images from a satellite, and it is because when the satellite looks at the Earth, the terrain moves at an apparent speed of 7 kilometers per second. That's 27,000 kilometers per hour. So it's going very fast. So it's hard to take an image that doesn't have a lot of motion blur in it. So we did several experiments to attack this problem, and one of them was to take many images with a very short exposure time, so each image didn't have enough light to be of acceptable quality. So what we did is to take many of them and to try to combine them to enhance the quality. This is a sample of one of those images. Maybe you can see the projector is not very good at this. There are not many different gray levels. There are about perhaps 6 or 8 gray levels, and there are a lot of these bad points. And with an algorithm to combine many images and reveal a better one, we could do this. that is quite better. We did some other things with this problem. Another thing we did was software deblur. This is kind of the ideal image we would like to get. And as we still didn't have a satellite going around the Earth, I had to simulate the images we would be getting, and this is a simulated image. You can see it has a lot of motion blur. It's traveling in that direction. The exposure time for this is about 20 milliseconds. It's a reasonable exposure time, but it is impossible to see anything there because of the motion blur. So I experimented with software deblur, and this was the result I got. I am rebuilding just the center of the image. And this image is the difference between the rebuilt image and the original one. So it is the error I made in reconstruction. The information content is the same as the original image in the areas that the blur image has nothing, so nothing can be rebuilt. But there is a bit less contrast here. That means that part of this was recovered, but not too much. This is not good enough, so we kept experimenting. We learned about a technique called coded exposure that consists in taking several images with different exposure times and therefore different motion blurs. And the exposure times are chosen in such a way that the parts of the spectra that become zero in one of the images are not zero in the others, so we can recover a bit of every frequency. So the result is a bit better. This is again the original image. This is a blurred image. This is a rebuilt image. Sorry. And this is the error. You can see that in the part that was rebuilt, the error image has almost just random noise. This random noise means that the features of the image are present, almost no details was lost, but the noise also means that the signal-to-noise ratio of the rebuilt image is a bit lower than the original. So this allows us to study the behavior of these algorithms and the quality of the images we can produce with them, and to assess their usefulness for actually rebuilding satellite images we can sell. The idea with all this is to show you what a Dynabook means for me. A Dynabook means a place where I can play with stuff for long enough to actually learn about the stuff I'm dealing with. We also built some hardware. We built a prototype. This is one of our mechanical engineers, and this is Hera, as you see. This is a prototype of a camera that sees the Earth. What you have below is a treadmill, a running machine that moves a photographic target we built with a piece of terrain. So the camera sees something like what a satellite would see. and this helped us do more experiments with these kind of programs. I also did a few more image processing things. This is rebuilding a color image from separate images for red, green and blue. This is not trivial because the images don't match perfectly, so we need to align them and resample them. This is a sample image of the thread mill prototype. And from this kind of images, one red, one green, and one blue, we were able to recover this. It's something. Well, the last thing I did was for our second satellite that will be launched in less than 1 month. And the problem here is that the images we take with our camera are 25 megapixel images, so they need 25 megabytes of data to store each pixel in 8 bits. And the radio link we have with the satellite is 9600 link, like an old 9600 modem. The older ones will remember how slow that can be. And we will be recovering packets that each one has only 200 bytes. So in some way we need to squeeze 25 megabytes in 200 bytes. That cannot be done, of course. Besides, the communication link is unreliable. That means that we maybe will recover some packets and maybe we will miss many, most likely. So we cannot use progressive compression. Progressive compression is standard, is used widely, and it is kind of giving you first a low quality image and then to add detail. But the detail is useless if the first part, the low quality image, is not there. The detail alone cannot rebuild an image. So we have to think something different for our satellite. Please give me a second. So what I did was a kind of random sampling. I did a way to extract thumbnails from these images that only use 200 bytes each, in two formats, one using 8 bits per pixel and one using 4 bytes per pixel, using a kind of floating point I did. And to sample the image in a random way so that some pixels will be there, even if we don't know which ones. So I resampled with several different zoom factors and at several positions in the images, and all of this is randomized in real time, so we really don't know. So I encoded in the header of the image the parameters used for this sampling, and this is one image of a run of this code. Unfortunately, you cannot see much over there, but you can see that these are the thumbnails. Some are bigger, some are smaller, and have different separation between the pixels. One interesting thing I did was, when sampling a part of this image, to look for the contrast. And if the part I was sampling had too little contrast, then I usually discarded it. So what I ended doing is to sample parts of the image where there was some interesting details to see. Those parts of the image were chosen with higher probability than those that didn't have much detail. Shall we? So, this is I will show you the result of this technique. This is the original image. It's a lot smaller. This is not 25 megapixel, but it's a kind of image we might want to transmit to Earth. And these are what I could rebuild with. This one was about 7% of the coefficient. This one. Sorry, this screen is giving me a bit of trouble. Okay, you can see that almost everything is there. We lose a bit of detail here, we lose a bit of detail here, but the algorithm could pick the areas with more contrast and transmit them. This is with about 7% of the coefficient, so it's not too much a high compression ratio, but and this is what we could get if we only get very few thumbnails. The parts with higher contrast are still there, and the parts with low contrast have almost no detail. So we expect to be able to, as we start to receive packets from the satellite, to quickly build images like this one, and as time goes by and we receive more packets from the satellite, we should be able to rebuild stuff like this. Well, this is all. Thank you. Questions?
So, do you mean to say that each 200 or so byte snapshot, this picture, will have sample points chosen at random, so that with each new one you get different samples and then you merge them in? Is that what you mean?
Yes, exactly. Not all points are at random. What is random is the top left point and the sampling interval. But each thumbnail is regular. Okay, so it's a pixel every 16, for example, and that goes in both directions. So at the header, the only data I need to encode is x0, y0, and zoom factor. And all that stuff goes in 8 bytes.
What we want is to get more detail as we get more data. So, and even if we miss any packet, we can still reconstruct every time with more data. So we need to somehow make each packet independent. The second one we didn't say, but has less than 1% of the image. Less than 1% of the image was transferred in simulation.
And even so, you can see something. A JPEG compressed with this level of compression is worse. At least over here. Maybe it looks like this everywhere, but at some parts we do have some more detail, and it's in the interesting part.
That part of the selection of the picture is written in Cuis or in C?
No, that's what it's good.
All the code that runs on Earth is Cuis. the code I did to control the camera and to prepare the images for transmission to Earth was done in the final version in Python. The satellite is running Python, but I use Cuis for experimenting and playing and prototyping all the code, even if afterwards it will be in Python. So Python is not my dynamo. My dynamo is Smalltalk.
I think there is time for one more question. Why Python?
When I saw him working on that, I used a few of his images. He's done lots of classes, but he was all the time on the workspace, combining stuff, trying new parameters and coefficient, and combining filters and putting them in the pipeline. Like with the audio, he had like a chain of 10 filters, one after the other, and he played with workspace. So he used Cuis pretty much as a playground to find out what to do, like an experimenting tool. Then, really, the final language is, at this point, once the algorithm is closed, you may not agree, but it's just an example, whatever you use. These are highly algorithmic, like it's processing. I mean, you could work on this class hierarchy and everything, but it's like a big blob of the fastest code you can write. We didn't have a script to run it.
The value of Smalltalk here is allowing us to do the experimentation and to learn.
It won't be Python at the end. It probably will be DSP or something.
Yeah, sure.
Okay.